Hi everyone, today we're going to be talking about solving absolute value inequalities, but first I have a quick warm-up for you guys, so please pause the video. Alright, go ahead and check your work here. So remember, to solve an absolute value equation, we isolate our absolute value term, and then we set up two separate equations, one with the inside set equal to the positive constant and one set to the negative constant. So here we have two solutions. So today we're going to be solving absolute value inequalities. So the biggest difference here is that instead of our answers just being a value or maybe two values, our answers are actually going to be an interval or maybe even two intervals. So we're going to do this graphically and algebraically, and we'll start with graphically. So here we're going to graph the left and the right sides separately, and then we're either going to highlight everything above the point of intersection if it's greater than, or everything below if the absolute value is less than. And so then when we do this, you'll see that your answer might be one specific area, like an interval between two numbers, or you actually might have two separate intervals, so we'll describe those separately. Or it's also possible to get no solution, or even maybe all real numbers. So there's a lot of different types of answers we can see with these types of problems. And then here's just a reminder, with any type of inequality, if you multiply or divide by a negative, you need to remember to flip your symbol. All right, let's give this first one a try. So I'm going to treat this left side and this right side as two different functions, and I'm going to graph them separately. So this absolute value of x plus 2, this has a vertex at negative 2, 2. So we can start with that. And the slope going to the right is that a value, which is just 1. So I'm going to do that with a couple accurate points going to the right, and then I'll follow the opposite slope going to the left of my vertex. And then the other side of my equation, I'm going to graph this. This is y equals 6. So it's a constant function at y equals 6. So it looks like this. So here we are looking for the interval or intervals where our absolute value function is greater than or equal to 6. So greater than meaning above. So that's going to be this interval and this interval. So I'm physically looking for where my graph is above my constant function. And because it does say or equal to, we're going to include the points of intersection in our answers. So now let's describe these intervals. I'll start with this one on the left. It is going to go infinitely to the left. So my left boundary is negative infinity, which is never included. But then it goes up until this x value, which is negative 6. And that x value is included because of the or equal to sign. Then I'm going to use my union symbol, and then for this next interval, this interval starts at x equals 2 and again is included, and it will continue infinitely to the right, so the upper boundary is positive infinity. So again, here we have a solution that is actually two separate intervals. Let's try another one together. So here, let's graph this absolute value function on the left first. Here we have a vertex of 1, 3. And then I can see that the slope to the right of my vertex is negative 2 because that's my a value. I can do this opposite slope to the left. And then here I have the constant function y equals 1. All right, so this time we again want the interval where our absolute value function is above our constant function, but if you look here, this time it's going to be a single interval instead of two. So the only time where my graph is above that line is here to here. Now it is just greater than, not greater than or equal to, so we're not going to include the points of intersection. So I can see that my lower boundary is at x equals 0. and the upper boundary of my solution is at x equals 2. So it's just everything between but not including 0 and 2. So again, like the last example, sometimes we have 2 intervals as our solution, or sometimes we just have a single interval as our solution. All right, so now we're going to talk about how to solve these absolute value inequalities algebraically. So we are going to start by isolating the absolute value term as much as possible, just like we did in the warm-up, and then we're going to create 2 separate inequalities, one for the positive and one for the negative case, just like in the warm-up. From there, we have to be careful about the setup of our problem. If our isolated absolute value is greater than, this becomes what we call an OR scenario. So when you solve the 2 separate inequalities, it can be this or that. There does not need to be any overlap in your values. However, if you have a case like this where your absolute value is less than, this becomes an AND case. So when you solve the 2 separate inequalities, there has to be overlap in your answers. It's your final answer is where your 2 separate ones overlap. All right, let's try this one together. So my first step needs to be isolating my absolute value term as much as possible. So I'm going to start by adding 5 to both sides. So now I look at this, the setup of this inequality, and I see that the absolute value is less than 12. So less than means and. So when I go to set up my 2 separate inequalities, I'm going to actually write the word and between them to remind me that there needs to be overlap in the answers. Now when I go to do the negative case, so I have the positive 12, when I go to the negative 12, I also need to flip my inequality symbol. So the symbol should be flipped for your 2 separate inequalities. Then from here, I can finish solving. So I have x is less than 7 and x is greater than negative 17. Now, since I have that word and, I have to figure out what values meet both of these requirements. So to do that, sometimes it's nice to set up just a really rough number line to visualize what's going on. So I need numbers that are both less than 7 and greater than negative 17. So here's negative 17, here's 7. Again, we want everything less than 7, so that would be like this, and everything greater than negative 17, like this. And again, we want ones that overlap for both of these inequalities. So that overlapping area you can see is right here between negative 17 and 7. So that is going to be my final solution. Here, let's write this in 2 different notations. Let's write it in inequality notation. So negative 17 is less than x is less than 7. And we can also practice writing that in interval notation. There you go. So there is another way we can set up these less than problems. So if you notice that after you isolate, it is that your absolute value is less than some constant, we can actually simply take this number, make it negative, move it to the other side, and add in another absolute or another inequality symbol like this. And then when we go to finish solving, here you can see that I would subtract 5. I would just do it to all 3 parts at the same time. And we get negative 17 is less than x is less than 7. So here you can see that we get the same answer. It's just a little bit more succinct and a little bit more efficient. So this method is great, but I do want to point out it only works when we have an absolute value that is less than. All right, let's try another one together. So here I'm going to, again, start by isolating my absolute value term. Here you can see that I'm going to divide both sides by negative 2. Since I'm dividing both sides by a negative, I need to make sure to flip my inequality symbol. So it becomes positive 3 on the right side. So here you can see that my absolute value is greater. So I always say greater means or. So when I set up my two separate inequalities, I'm going to separate them with the word or. And same as before, when I go to do the negative version, I'm going to flip the inequality symbol here. So now when I have my two intervals, there does not need to be any overlap. Or implies that they can be separate. So here I'm going to add 3 to both sides. And I get x is greater than or equal to 3, or x is less than or equal to 0. So just to visualize this, we could see that this is just two separate intervals. Here's less than or equal to 0, and here's greater than or equal to 3. And because, again, it's an OR scenario, we do not need any overlap. If they do overlap, that's okay, and it actually ends up being all real numbers, but no overlap is required. So if we were writing it in inequality notation, we would actually have the word or in our answer, this, or you can use a union symbol, or we could write it in interval notation, negative infinity to 0, or 3 to infinity. So just be careful, again, when you have an or, a greater, it means or, and when you have less than, it means and. And requires overlap, or does not. Alrighty, go ahead and pause the video and give these last two a try on your own. All right, go ahead and check your answers really quick. So part A, this is greater, so it's an or problem. So I have my two separate inequalities. Make sure you flipped the inequality for the negative version. And then when you solve, you get x is greater than 2 or x is less than negative 4. So you can write it in inequality or interval notation. And you can see there is no overlap, but you don't need it for an or problem. Now for part B, it looks like a greater than problem, but remember you have to isolate before you decide. And in that process, our inequality symbol flips, so it's actually a less than, so it turns into an and problem. So we do need overlap in the two. So we need numbers that are both less than or equal to 1 and greater than or equal to negative 1. So you can see that I visualize that here with this number line. So our overlap is between negative 1 and 1. Alternatively, you could have just put this on the other side and made it negative, and you would get this answer here. So that was that alternative way that we can set up those less than problems. All right, that's all for today's video. Thank you so much for watching.